All right, so do actually have a couple of requests this morning, and so one of them is about the lab that's being done this week, and this is the rates of reaction. So it's a little bit ahead of where you are, but definitely the thing that's kind of manageable. So the lab you're doing this week is looking at, you're measuring the rate of a reaction. In this case, the rate of the iodine clock lab, and you're trying to figure out what the order is for the different compounds. So you've got two compounds, I think it's potassium iodide and the thiosulfate. So method of initial rates. As the name implies, we're going to have rates. And what we're going to do is we're going to create a table. And the easiest is if you have just 3 runs. So run 1, run 2, run 3. And you've got some reagent A, B, and their concentrations. So let's say 0.1, 0.1, 0.2, 0.1, 0.1, 0.2. So these rates here are measured numbers. A and B, these are the concentrations in molarity. So how does method of initial rates work? Well, in order for method of initial rates to work, we first have to make a guess as to what we think the rate law is. The easiest one to work with is a power law, so we're going to assume we have a power law. So our power law in this case is going to be that the rate is K, concentration of A to some power alpha, B to some power beta. But we don't know what alpha and beta are. Now, the thing is that we assume this. We do not know if this is actually a true statement. So alpha and beta here are what would be referred to as the apparent orders. Apparently, it's this order in this range. Because there is no theoretical justification, meaning that there's no reaction mechanism to back this up, we're going to have to say that it looks like this. So that's what the apparent means. It looks like this in the ranges that we studied. Now, I'm going to show some manipulation beneath this, and it's a lot of algebra, but it is building to a point. So method of initial rate says if we change the concentration of one of the reagents, we can tweeze out the order. Now, some professors teach this by saying we'll double the concentration of one and see if the rate doubles, quadruples, things like that. There is a way to estimate the order out of that. It is, quite frankly, a bad way to do it. It is a bad way to do it because we can get this algebraically. So what we can do is we can say, well, let's take the ratio of 2 rates from 2 different runs. And we're not going to specify what they are, so we're going to call them run little a and run b. So RA and RB here would be measured. Actually, let's do I and J. Run I and run J. Now, these still have the form K, A for run I to the alpha, B for run I to the beta, all divided by K, A for J run, B for J run. Now, the K's here don't change because the temperature is constant, so we can effectively cancel it out. And if I bring this down, I can use a property of powers. It says that any number, 2 numbers raised to the same power is just the ratio of those numbers raised to that power. So I end up getting, I'm sorry for the light there. Go that way for just a minute. We get the ratio of the rates is the ratio of the concentrations raised to the alpha power times the ratio of the concentrations of B raised to the beta power. If we take a natural log of both sides, we can exploit the property that the natural log of the product of 2 numbers is just their sum. And the further property we can exploit is that any number raised to a power within a natural log is just bringing that power out. So we'll end up with this formula. The natural log of the ratio of 2 runs is the apparent order of reactant A times the natural log of the ratio of its concentration between the 2 runs plus the apparent order of B times the natural log of the ratio of the concentrations between the 2 runs. And so this formula here is what we exploit with the method of initial rates. So if we keep 2 concentrations constant, I'm going to get rid of this algebra down here. So if we compare run 1 into run 2, We don't know what the order is on A yet, but it would be the natural log of 0.1 over 0.2. So if we're going to compare runs 1 and 2 here, the first term is the apparent order of A times the natural log of 0.1 over 0.2 because it's run 1 over run 2. Plus beta, natural log of 0.1 over 0.1. Now, 1.1 divided by 0.1 is just 1, and the natural log of 1 is 0. So if we keep two concentrations constant, so if we keep the concentration of B constant or the concentration of A constant, that term disappears out of this equation. And we get that the apparent order is the natural log of the two runs divided by the ratio of the concentrations. So that's how we can get the apparent order of A, is that for this particular experiment, is that we just take the natural log of rate 1 over rate 2 divided by the natural log of the concentration of A between run 1 and run 2. And this will give us a number. And the same thing is true for the apparent order B. If we look at run 2 or run 1 versus run 3, we would get that the apparent order B is the natural log of run 1 over run 3 divided by the natural log of the concentration between runs 1 and 2. Now, there is philosophical debate on this. What do you report alpha to? Now, some textbook or the orders. So what do you report orders to? Integers, or do you report them to decimal points? Now, there are two schools of thought on this. And the first school of thought is that they should be integers. This is kind of a circular argument. So it is true that for an elementary reaction, the orders have to be integers because because of the proof of where that rate law comes from. That said, we don't have proof that this is a power law reaction. We just assume that. So while it is true that a power law should only have integers in it if it's derived off an elementary reaction, this isn't necessarily an elementary reaction. For all we know, this is some complicated Taylor-Riddell, Michaelis-Menten. Like, there's a whole long list of common reactions that do not obey this forced fixed integer order. So my school of thought is, unless you see it explicitly stated otherwise, is that you report these orders to 3 sig figs. So if you get 0, it's 0.00. Or if you get 0.01, you report 0.0100. The reason you do this is because these are apparent orders. You don't know if this is truly a power law relationship. So you need to reflect how well you know it's an integer. If you get 1.01, report 1.01. If you get 1.00, then fine, report 1.00. But don't just round it to an integer, because you'll definitely come across situations, particularly if you look at the practice packets, where you'll get like 1.5. Those problems are designed to give you fractional orders. They're not truly integers. What you're probably seeing is something that doesn't really obey these power law kinetics, and you've kind of force fit the model to make it work. So these fractional orders here tell you that it's not truly a power law relationship, at least not on the regions you're looking at. So that's how you do the lab. You create these tables of rates of reactions and the corresponding concentrations of the different reagents. And you compare runs where one reagent's concentration is held constant, and you just take the natural log of the ratio of the rates and divide it by the natural log of the ratio of the concentrations of the reagent that changed, and that will get you the apparent order of whatever thing's concentration changed. Now, another question I received was regarding graphical analysis of kinetic data. And the question I'm getting is a very common mistake I see with students, and it's not, it's more trying to equate things that aren't equal. So when we look at the solutions to the 3 kinetic equations, so we have 0, first, and second order. For a 0 order reaction, the concentration is the starting concentration minus kT. So that's 0 for first. Concentration is starting concentration e to the minus kT. And for the second order, the concentration is actually a complicated algebraic function, but for simplicity, we use this form. Now, we can linearize this form here by taking natural logs. And if we linearize this form, we get the natural log of A equals natural log of the starting concentration minus kT. So these are the linear forms of the solved 0, first, and second order equations. The thing to keep in mind here is that this is y. This is y on your axes. Drew that poorly. Time here is x. So if we want to force fit this to a model, or we want to look at a model where it's y equals mx plus b, this tells us that these terms here are the y-intercept b, and in all of them the slope is related to the rate constant k. So on the homework, you're going to see, particularly with the easy problems, it goes ahead and gives you the plots. A versus time, natural log of A versus time, and whatever the concentration of A versus time. Now, these are hypotheses to be tested. So if we have a reaction and we just measure concentration versus time and we get a straight line and we fit it and we get, like, it gets really good, it's non-random errors, it looks like a straight line, it's got a really high R² value, we know that it's a first order reaction. And the reason, or zero order reaction, the reason we know it's a zero order reaction is that if we take the same data, we take the natural log of the concentration versus time, we wouldn't get a straight line. Or, oh, sorry, I drew that wrong. That's the way it would look for a zero order reaction. For natural log of A versus time and then 1 over time, we would end up not getting straight lines. So if we do these three plots and we look at it and the concentration versus time is the only linear plot, that's a zero order reaction. If we look at this data, if we look at concentration versus time and it's not a straight line, but the natural log of that concentration versus time is, and whenever the concentration isn't, it tells us the reaction is first order. If we look at concentration versus time, it's not a straight line. And we look at natural log of concentration versus time, it's not a straight line. But we look at 1 over concentration versus time, and that's a straight line, then we know it's a second order reaction. So the first thing we do with this kinetic data is we use these three sets of data and we see which plot is linear. If the concentration versus time is linear, it's a zero order reaction. If natural log of concentration versus time is linear, it's first order. If 1 over concentration versus time is linear, it's second order. The thing is that you will never get a false, you'll never get one where both, or 2 or 3 of them are linear. Only one of them will ever be linear. Now, the hard part is interpreting the data. So I'm just going to draw straight lines on all these. So we've got a straight line, and we've got a straight line because theory predicts we should have a straight line. The other thing that theory predicts is how the values corresponding to that straight line can be translated into useful kinetic information. So if we have concentration versus time, we will fit it to an equation. We will get y equals mx plus b. So if we go to this, y is concentration of A, which we know that's the y-axis. X here is time. We know that because it's the x-axis. And what it says is that the slope here will be negative k. So if we know the slope, we know that the slope equals k, and we know the slope's going to be negative because k is a probability and probabilities have to be positive. We also know that the y-intercept here is the starting concentration. Now there's a way to intuit that. At time equals 0, if you look at the equation up here on the top left, concentration equals starting concentration. For natural log of A versus time, we will still get a y equals mx plus b. Y here is the natural log of the concentration. We know that. That's what the plot is. X here is the t. The slope is also negative k. B here equals the natural log of the starting concentration. And this is where the confusion comes from. The natural log of B does not equal the starting concentration. That's not what the theory is telling you. The theory is telling you that the y-intercept here, B, equals the natural log of the starting concentration. So let me... So if you want to find the starting concentration, you have to get rid of that natural log. If you take the natural log of B, you're just taking the natural log of the starting concentration. So here you would have to take the exponential. And so E to the B is your starting concentration. We look over here, 1 over concentration versus time. Again, y equals mx plus b. Y is 1 over concentration. X is our time. Our slope here in this case is going to be a positive k, as predicted by the theory. And our slope, our y-intercept here, b is going to equal 1 over the starting concentration. So in order to find the starting concentration, we take 1 over b. We invert it to get it. So this is how you can extract out the starting concentration and the rate constant k from 0, first, and second order models. All right, so those were the only 2 questions I had asked in advance. Are there any questions from those of you who are watching the stream right now? Oh, I respond to a quick email. No, we discussed when using the method initial rates, what if the concentrations are different instead of constant? Could you work with that? In principle, yes. It would just be an utter nightmare. So let's say for whatever reason you had just you didn't set your experiment up right. Oh, you still need 3. So let's say for whatever reason you did something like this. You would still be able to work with this formula. So you would just arbitrarily pick 2 pairings. And now you have 2 equations and 2 unknowns. So here's your alpha and here's your beta. So in principle, you could solve for either alpha or beta in this equation, plug it into here, and then solve for the other one. So you get something like alpha equals ln R2 over R3 minus beta ln B2 over B3 divided by ln of A1 over A2, A2 over A3. Plug that in for alpha. These are all numbers, and you could solve for beta from the first equation, and then once you know beta, you can stick it into this equation and solve for alpha. It is doable, it's just a ton of algebra. So this is kind of why we design experiments that we only control only change one variable at a time, is to kind of keep us from having to get to these daunting algebraic expressions. But definitely if you had any 3 rates given at 3 different sets of concentrations, you could definitely figure it out. It's just a lot of work. Yeah, you're welcome. Yeah, I worked with the graduate student at Stanford. He was really problematic to work with, and he tried to do this and then never changed the ratios. So when he conducted these experiments, basically he didn't have, because the ratios were always the same between the two runs, he couldn't solve it. This is why you always put a little bit of forethought into your experiments before you conduct them. Oh, okay. So one more thing I need to answer to. So on the course website, there are 2 Excel sheets that you need to download to do the homework. And let me make sure I find them first. They should be under the Lessons tab. Ha, wrong course. So let me download them first, and then I'll talk about how to work with them. So in terms of the course website, this is what you're going to see: data for homework assignment, test 2 pre-exponential factors in the A, and test 2 concentration versus time. So for these problems, basically what this is doing is forcing you to do the data processing. So this is what data set 5 looks like. And students get into this really nasty habit when they take this course is they don't really connect the dots that data is a real thing. This is what we measure in the real world. So we measure time, concentration versus time. In this case, we could use it using spectroscopy, something like that. But when we talk about these 1 over concentration versus natural log concentration plots, they genuinely think that's what you're measuring, is you're measuring natural log concentration versus time, and you're not. So what this homework set is asking you is what is the order of this reaction, and what's the rate constant contained, what's the starting concentration. So to figure out the order, you would need to look at the natural log of concentration versus time and 1 over the concentration versus time. So if I plot concentration versus time, you always want to work with a scatter plot. We get this function. And do a quick layout. So this is our first plot. What we're going to do is going to add a linear regression to it. Big things up here: display equation and chart, and display r squared. So if this is my zero order reaction, let's see. If I want to do first order, I just switch it to natural log. And then we need to do 1 over concentration versus time. So these are the 3 scenarios: second order, zero order, and first order. I know they're a little hard to see on the screen. It's the best I can do for you. But if you take a look at it, the r squared here is best for the natural log versus time. So that tells us then that this is a first order reaction, because if we look at the zero order and the second order, this r squared is lower. On top of that, it's hard to see here, but if you were to do the residuals, which is basically the errors between the line and the data points, you'd see that this is consistent. This goes low, high, low, the same thing here. So this is the first thing you have to do with this data set, is look at these 3 plots and figure out which plot plot fits it best. In this case, the natural log of A versus time fits it best. So that tells me that this is a first order reaction, and I can just kind of get rid of these plots, these other 2. Now, question is, what's the starting concentration? Well, there's 2 ways to do the starting concentration. One is that we can recognize that B is the natural log of the starting concentration. And so e to the b, in this case, minus 1.3984 is our starting concentration. Now, the other thing we could do, and a student pointed out to me, and this is kind of embarrassing, but it is like losing forest in the trees here. You're also giving the starting concentration right there at 0.250, so you can easily do that. The other thing I ask you for is K, and K here is the slope. So the slope here is 0.0048. That would be your K value. That's your rate constant. So this is how you approach all of these, and honestly, if you know a lot about Excel, this gets really easy. You can just drag and drop all the formulas in, do the 3 plots for all of them, and extract out K pretty quickly. So this is how you do this concentration versus time homework. The other one is K versus temperature. Now, we haven't quite gotten to this point yet, but K here has the form A e to the minus EA over RT. And this is called the Arrhenius equation. So let me talk about this really quick. And we haven't quite gotten to this. Oh, stop it. So with the Arrhenius plots, if we know K equals A e to the minus EA over RT, let's switch back to the black pen because that reads a lot better. If we take the natural log of K and we do some rearrangement, we get that the natural log of A minus EA over R times 1 over temperature. This is our Y. This is our X. This is our Y-intercept. And this is our slope M. So B equals ln of the pre-exponential. And the slope here equals minus EA over R, where R is going to be 0.008314 kilojoules per mole Kelvin. So what you have to do with this K versus temperature data is you're trying to extract out EA, which is the activation energy. So to do that, we need to have 1 over temperature, and we need ln of K. So the ln of K is pretty easy, just the ln of that number. And 1 over temperature is going to be the temperature in Kelvin. So if I plot this, at the trend line, I get that the y-intercept here is 8.4471, and the slope here is -6. 527.6. So your pre-exponential factor is e to the b. So it's just going to be the exponential of that number. Your slope is minus EA. Come on, it's just text, not a formula. So then, in order to solve for EA, it's going to be negative m times r. So it's going to be negative that number times 0.008314. So the activation barrier here is 54.3 kilojoules per mole, and your pre-exponential factor is 466, or 4,660. And that's what you do for all of them, is that you just turn around and convert K to ln of K, temperature to 1 over temperature in Kelvin, get these linear plots, and extract out the activation barrier in the pre-exponential factors. Now you should kind of see this with the homework. So one of the homeworks kind of gives you that already. It gives you ln of K versus 1 over temperature and asks you to extract out the activation barrier in the pre-exponential factor. The next homework says you need to do the plots yourself, and this is to give you experience with doing the plots. Now in the CETIC course, we do give you a little bit of experience with measuring the EAs. And what you do is you do the iodine clock lab, but you do it at different temperatures. So we do it at room temperature, we do it 0 degrees C, we do it at 40 degrees C, and we do it at 60 degrees C, and you generate your own Arrhenius plots. You don't really have the ability to generate those types of temperature baths at home, which is why you don't do that experiment. But I can tell you from personal experience, I've done those personal measurements. Like I've measured K versus temperature and used that to extract out an activation barrier. This is something you definitely would see if you try to do some type of kinetics experiment. But the big thing is breaking this idea that the theory is not connected to anything that goes in the lab. In the lab, you would figure out what the rate constant K is. You would measure it at different temperatures, and then you would use this Arrhenius plot to track back out what the activation barrier is. And one thing I really wish we could teach more in depth, we're just not at that level in the course, is that if you look at ln of K versus 1 over temperature, sometimes you will see this effect. So here you see one line, here you see another. What we see here is that the rate limiting step has changed. The mechanism has changed. So because we see this shift in the ln(k) versus 1 over temperature plots, we can actually see when mechanisms change or some feature of the mechanism changes. So all evening accuracy really isn't too bad with this. So the iodine clock lab is actually really well behaved. So you should be getting around first order for both of your reactants. But when it turns black, for low concentrations, it's a little hard to see. For high concentrations, it's pretty definitive. It should just turn like jet black. But that said, with the low concentration ones where it's a very faint black, that's also a very large stretch of time. So even though you may be off on the exact second, because it's such a large time delay, basically that kind of like gets buffered out. Yeah. If you get enough reagents, you can try it again. If not, like, just do your best. Again, these are kind of home experiments. There's a lot of tolerance built into them, or a lot of tolerance built into what you report. Actually, the worst one is when we do the 60 degree C run of this iodine clock lab, because it doesn't turn blue, it turns brown. And you have to see the brown against the steel. It's a steel hot water bath, so you have to see the brown against that. Generally, what we've tried doing in the past is we just take a sheet of white paper and put it in a Ziploc bag and push it underneath the water and hope it doesn't get wet. So why don't we, so the question just got asked, if they're determined experimentally, why not just use something like method of initial rates all the time? So this is where we get into engineering versus science. Method of initial rates requires you to guess what the rate law looks like, and you may be wrong. Particularly with something like when there's a catalyst involved, they're never power order relationships. So the most famous example here is Michaelis-Menten kinetics. So you have two gases, so gas A and gas B. So, oh wow, that was really poorly written. So this is not Ehlers-Danlos, it's not Michaelis-Menten, it's Langmuir-Hinshelwood. So these are Langmuir-Hinshelwood kinetic models. The theory actually predicts what is seen experimentally, and what we see with the rate of reaction. So if you look at the mole fraction in the gas phase, the rate of reaction does this, and there's a sweet spot. So the reason why we would want to do why we want to start working with coefficients and why we want to start working with the mechanism is that it can give us an actual rate law. We can figure out what's going on. And once we know what the model is, we can fit any data to it. So again, we're just kind of doing really introductory kinetics here. We're not really going super in depth into how you do this type of analysis. But having a model is better than not having a model at all. Because the one thing they really love to do to piss off engineers in their kinetics courses is they say, okay, given method of initial rate data, how do you know it's this? How would you prove that something is really first order or second order? And the answer is always, we'll double the concentration or cut the concentration in half. And what you should see is, you should still see that zero in first or second order behavior. One really obnoxious feature of first order reactions is that if you solve the diffusion equation, so let's say you have a reaction that's being done in water, and really what's limiting the reaction is the diffusion of reagents. You're just not stirring enough. It will look first order. So if you solve the diffusion equation, you get a first order model. So another question they love to ask, how do you know that this just isn't a diffusion limit reaction, that it's really not first order, it's second order or some fractional order? This is why we need the models. They do a really good job of giving us ways of predicting what could be going on. Yes, the iodine clock lab takes a long time. That's kind of on the longish end of these labs just because of how many runs you're having to do. Generally speaking, it shouldn't take you any more than 2.5 hours to perform the experiments and maybe an hour or two to do the data analysis. That's pretty typical for most labs. It's the summer, we're doubling up, so if it feels like you're doing a lot, it's because you are doing a lot. Regular semester, we also do 2 labs a week. So this is the practical, so now I'm pontificating here. So part of the reason why we want models is that they can give us a better idea as to what we should actually be fitting into. Just blindly saying power law, you're probably not dealing with a power law. If you do something like Langmuir-Hinshelwood kinetics, you can actually like tweeze out what those parameters are by manipulating the data. So by having a model, you're more likely to have a fit that actually works more globally than just on the regions you do the concentrations. Now, practically for method of initial rates, method of initial rates has a ton of assumptions built into it. And the biggest assumption built into it is a derivative. So your rate is dA dt or something like that. But the thing is that dt in calculus here is infinitesimally small. That's not possible. So what we measure is concentration versus time. In principle, we know the initial concentration. We can measure that as we go in. But how long between the concentration and the first time point? Because you can't measure instantaneously fast. Like you can't take an instantaneous derivative. So generally there is a time lag here. And for zero order reactions, it doesn't matter how big the time step is. So this is something that I don't know if it's proven in the notes. I used to have it proved in the notes, probably not anymore. But for a zero order reaction, it doesn't matter how big this gap is between 0 and the first time where you measure the concentration of A because it's not going to go any faster. But if you look at an exponential, so a first order or a second order, anything that's non-zero, you actually start getting errors built in. So you tend to underestimate the rate, and it's going to get worse and worse and worse and worse as the time steps get bigger and bigger between the initial concentration when it came in and when you measure the concentration coming out. So this is an inherent limitation of method of additional rates. It always underestimates the rate of reaction. Because we get that underestimate, we know any numbers we get are suspect beyond that. So practically in a lab, method of initial rates is great for verifying a rate law. It's not very good at proving one because we never actually know what the initial rates are. And actually, so again, I hate to like keep propping up like the CEDIC course because we realize this pandemic, that's why we're doing this online stuff. There is a lab where we get students to compare method of initial rates to the graphical analysis, and they give similar answers, but they definitely give different answers. So even with graphical analysis inherently assumes that you have a zero first or second order. It inherently assumes that your power law is correct. And in the notes, there's actually plots to show you that you can get pretty far away from a zero. You can have something that's really a 0.9 order or a 1.1 order. Graphical analysis can't tell you that. And this is a model that I built and I ran. Graphical analysis will still say it's first order, even though the model is definitely not first order. It's clearly not. It can't tell the differences. So I realize that was a lot to say there, but we kind of need both. We need the theory to give us a model to fit the data to. Method of initial rates, graphical analysis, all these kind of have built-in assumptions to them that tend to fail. So if you don't have both, you have a very incomplete picture. And typically engineers do stick with the MOIR method or graphical analysis because they don't care. They just need numbers. But if you want to do any type of like reaction engineering, you want to know if one catalyst is better than another, or if you want to know if one reactor configuration is better than another, you need models. Otherwise, it's just numbers. Yeah, it was something we also, particularly with if something is better, a catalyst is better than another, you may have a reaction that runs slower even though you add a catalyst, but if you really work it out, the activation barrier is lower. You just didn't have a really well dispersed catalyst. There's a lot of things that go on inside a reactor. Yeah, he tells us like my favorite section to teach. Again, it's way more information you need for the exam. Richard Ernst died. No, I knew him. Well, I met him. I won't say I knew him, but I met him. So there's a question you got to ask. Where graphical analysis and method of initial rates got radically different answers. Which one is more accurate? It depends. So this is why why it helps to have a model. Method of initial rates has more error built into it. And it has more error built into it because you're relying only on 2 data points. And if you measure those 2 data points incorrectly, you're going to get a wrong slope, which is going to translate into basically an incorrect prediction of order. Graphical analysis uses all the data points. So let's say you took a measurement. So we got concentration versus time. And that's your starting concentration. And then it does this. So you can look at this data and you can see like obviously there's something wrong here. Like maybe there was a lag in the reaction, like there was something going on here. But method of initial rates is going to say, well, this is a really slow rate, so it's probably 0 order. But if we look at graphical analysis, it's going to say first order. So first of all, to figure out which one is probably more right, method of initial rates has a lot more error built into it because it is highly dependent on the first and second data points. If those aren't measured correctly and they aren't measured quickly, you can get massive underestimates of the order. That said, graphical inherently assumes that it is an integer reaction. So it's a 0 first or second order reaction. Because it makes that assumption, you may have a truly fractional reaction and it's just not going to work. So you may plot 0 first and second order off of this data and realize that none of them are linear plots. And yes, this does happen, particularly when you look at something like non-power law relationships. So the method of initial rates there may, even though it may give a wonky answer, it may be more correct because it's not inherently assuming that it's an integer order on that reaction. So to answer your question, which one's more accurate or less accurate, it depends on the circumstances. Graphical is going to inherently assume that it's an integer order. If you have a good reason to believe it, it's going to be the more accurate one because it uses all the data points. So the wonky data points kind of get averaged out. If you don't know for sure that it's an integer reaction, it's an integer order, method of initial rates is probably going to be better because it opens up the opportunity. That said, because it's so dependent on the first two measurements being taken, it's more prone to have bigger error bars. Yeah, you're welcome. I do enjoy these questions, and again, like I hate to keep qualifying with this, but like we are just kind of doing an intro to kinetics. We're not doing like a full-fledged kinetics course. A full-fledged kinetic course would like go into all this analysis, and not only would you have this explained to you, you'd also have to prove it, which sounds daunting, but actually it's really kind of nice. Like in my opinion, it made a lot more sense after I had to explain why things were happening. Other questions in our remaining 10 minutes? 9.5, but still. I think they're using rate expressions and rate laws synonymously. So yeah, it's... But yeah, I was taught rate laws. This is the chemical engineering background showing up. I think chemists call them rate expressions. He said that. Look it up. Oh, wow. That's a terrible way to write that. Yeah, rate expression and rate law are the same thing. I think they're trying. Looks like some textbooks are trying to imply that a rate expression is like the numerical value, whereas the rate law is like the formula. Oh, stop teaching that like that. Chemistry labor text. It's an awful way to teach it. Yeah, I'm looking at like, yeah, it's rate law. The first one I ever had to work with was what was called an exergy analysis. And I spent like 3 months trying to figure out what on earth this professor was talking about with exergy. And basically, if you have a system and you want to know like what's the maximum work you can get out of it, people generally define it to absolute zero because that's a really easy reference point. Like the energy you have relative to no energy at all. And this just kind of shifts it to room temperature as the reference. But he kept talking about exergy like it was this radical new idea. It's like it's actually just kind of what we normally do. It just we use a different reference. It's a better reference, arguably, but it like he just kept saying like, oh, it's not. I forget what the other analysis is called. But he kept like saying like it was really different. When I really like read his book and everything, I was like, no, they're the same thing. You just have changed your reference point. And arguably, yes, it is a better reference point. But like it made so much more sense when I stopped thinking about the way he tried to explain it. We're coming up 11:59, so again, if you ever have questions, feel free to email in advance. It really helps pass the time. These are always posted after they get done, so thank you for coming. And I will see you all tomorrow.